welcome to the stream. I hope some of you followed my scheduled session rather than relying on the social media post because I just posted like 2 minutes ago. Anyway, I'm excited about today. Today we're going to pick up where we left off. We were creating a parser, like a front end for our compiler, because the book, Essentials of Compilation, does not include a front end as part of the text. It does include it in the support code because, you have to parse text into data structures. So they likely parsed it into lists, using a typical reader type of interface with that comes with Lisp projects, Lisp languages. But we're doing a more classical format, and we're going to take what we've gotten from the tokens today, and we're going to turn it into AST. So that's the goal for today. Last time we had some fun with dealing with greediness. I say fun in a little bit of an ironic way, because greediness is an essential part of constructing lexical analysis. You have to decide where you use a greedy match and where you use a best effort match. And the problem we were running into was that I didn't understand exactly the way nibble worked, which is when you give it a list of tokenizers, it will try them in order, but it's not going to yield a token until one of the lexers, any of them, returns a complete token. So the problem was that, and I'll go ahead and pull up the code here so we can start talking about it. So this was our lexer, and we have a problem with the fact that there's this lexer variable, and when we looked at the innards of that, and let's just go to definition, it's pretty straightforward. It says here we're going to have an identifier lexer, and the identifier starts with any lowercase character A to Z, and then it can be followed by any character A to Z, including caps, numbers, and underscores. So this is a pretty typical thing used in a lot of languages. Now Lisp is a little bit less fussy with identifiers, and I think that what we might consider doing is turning the identifier into a more generic thing, and then using the toValue function, if we want to go back and redo this, but using the toValue function to determine is this a keyword or not. So what we found was that if we go into the implementation of identifier here, it will look at, so it constructs a string, constructs a regular expression from the start and the inner, and this is like what should match the entire identifier, right? You have at least one character from the start set, and then you have any number of characters from the inner. And then you make a regular expression just for the inner part, or for the extension of the identifier as well. So, so if we get the look ahead and the complete lexeme, so this is like the collection of all the characters that have been accumulated so far. And if it says, if both of them match, then skip. That says keep, this look ahead. Excuse me. This look ahead matches, so you want to keep accumulating. That's what this skip means. I honestly, if I were doing this, I'd probably say Okay, so they're saying skip any additional matchers this iteration, add the next grapheme. So this is a little bit greedy, and the true says, you know, that this pattern here, where both of them match, says that we should continue trying to accumulate an identifier. If the look ahead does not match, then it says, does this contain a reserved word? If not, then you keep it, and this is the identifier. If it does, then you say no match, because you're going to be matching that with something else. Okay, so that's the pattern of this, and regardless of whether the look ahead matches, if the if the lexeme doesn't, that's the only case here that we haven't covered, right? The lexeme doesn't, or the look ahead, you know, doesn't matter. Then there's no match. So we're saying this lexer will not match. Now the problem was, if we also look at what we were doing here. So keyword, if we go to keyword, this says that this string is an exact keyword. Now you'll note that this breaker is like, what do you use to determine what's not valid? Or like what's the boundary character or a set of boundary characters for this keyword? So this one does not operate like identifier does, right? This one says this is the entire string we're trying to match, and then here's where we will stop trying to match. Okay, so this relies on the fact that, notice there's no skip here. If I were to change this, I would expect, partly because of what you consider keywords and like the role that they hold in your language, you would expect to try to often like greedily match on keywords. So as long with this one, I would probably look at, is the lexeme a prefix of this keyword? Now they're saying here, you know, example let and letter, you don't want, you know, that to be split. So that's why this, you know, this breaker argument exists, is to distinguish between the word let, if let is in your language, and something that is an extension of that word, which should not be parsed as a keyword and then something followed. So a good example here is like white space or punctuation. You might use to separate this keyword from something else in your language. What you don't want is to produce you know, a list of tokens that has let and then the extension of that word as a variable, for example. So I understand why this one is the way it is, but if you use this in combination like we did with the variable one, which is more open-ended and will like slurp up as much as it wants, then you get into a situation where if the entire keyword is not there yet, so in our case this is the keyword EQ question mark, which honestly I don't know why they use that and not the equals, but whatever. This is a situation where this prefix before the question mark will get matched by this. And then you'll see that the question mark cannot be part of this variable. So it's like, okay, I'm done. I've got EQ. And then you have a dangling question mark. Now, I assumed going in last time that that the order mattered here. And often what you'll do, like if we're writing this with leaks, the Erlang lexer generator, I would probably put EQ question mark well above anything else, and the order would be respected there. So long story short, we had to write a custom matcher that was greedy. And by greedy, I mean if the current accumulated lexeme is a prefix of our keyword, then keep trying to accumulate, right? If it's the complete keyword, then keep. Otherwise, no match. Now, what I might consider doing is rather than using this built-in variable, we can look at the support code for the book and see, is there a more relaxed version of this? In which case we could punt on some of the interpretation until we get a some kind of full value there, because I could see a case where you might want to have a function called eq int or eq rational, or specialize something. This is completely spitballing, but what our current lexer would do is it would split those. So you would have eq as a keyword, and then rational is a variable, an identifier. So maybe we need to think about what are the contents of valid identifiers, because honestly, even these built-ins are identifiers in some sense. We just decided to interpret them as reserved words. So so let's look at the support code real briefly. I do want to get to parsers. So this is the library we're using in Gleam called Nibble. It has a parser implementation in there. Looks like we have some combinators there that we can use to combine some things. That's nice. Okay. So let's look at the, I don't have it up here. We're going to go to, you compile a course. There we go. We're going to look at the support code in Racket. And they said that there was a parser in here, so we just need to find it. Let's look at the README, see if there's anything in there. Right, okay. Maybe it's in utilities. Okay. Debug level, test verbosity. So struct definitions. Okay, that looks like it's just making things nicer for working with it in Racket. Okay, and we will get to loops in the next chapter when we go to do that. There's like while and begin and so forth. Okay, looks like we need to keep going because I think that this is about pretty printing things, right? Because they're using like write string and so forth. Let's keep going. Value struct definitions, predicates for contracts on structs. Parsing X expressions into abstract syntax trees. Okay, so they have a bunch of things that are primitives here. So okay, and looks like they, they're defining patterns with the backtick, so that when that matches, that's like, it makes sure that this doesn't get interpreted as a keyword. It's like, hey, you want to look at the literal word let in here. Okay, and so then they're constructing the let from the abstract syntax tree from that. Let's see if they have a lexer here anywhere. Parse def, parse program, unparse, printing, x86, no. Okay, define syntax rule, while condition body. Okay, so this is a macro for transforming this pattern into something that's actual Racket. And they use the Y combinator there to compute a fixed point. I'm looking for how is it lexing, and it could be just that. Okay, so here's read program. So input prog, define input prog, call with input file path is a lambda, and it's doing back, right. So they're using Racket's reader to construct, and this is again a macro escape, and then for the list of, okay, so as long as this reads a new token, I'm guessing. What is this import? It probably is part of this call with input file. I bet this call with input file is a macro as well. It's basically saying, escape this list and wrap it in this program list. Okay, so they're making use of Racket's read function, which makes sense because that's like something you don't have to write in Racket. Now, what we could do is also, they have support code for the Python version as well. So let's look at that. Python student support code. So let's see, they don't have a special grammars.txt. I don't know if this is actually used by anything. Let's look at utils.py. Maybe we'll make use of the GitHub thing here. They've got a bunch of structures for holding things. Okay, I don't see anything about parsing in here. Let's see. Symbols. Okay, let's look at their compile function. So they've got a parse function. Where is that? Okay. Lark parser front ends. The question is, which one was that imported from? Which of these files? Oh, they got an early parser. That's interesting. LALR parser. Let's just go here. Okay, so this defers to parser, which is probably one of those. Okay, so they've got a grammar.py. Here's their Lexer. Let's look at their Lexer. Okay. Value flags raw. Okay. Pattern, string, pattern, regular expression, terminal definition, token. Okay. A string with meta information produced by the Lexer. So type value. Okay, so this is just a structure. Line counter, unless callback call chain. Okay, so scanner takes the terminals, regex flags. Okay. Okay, this function virtually tries less and less groups until it's successful. Okay, so their Lexer looks abstract. Okay, so they do this next token thing. And it calls self.match, which calls the scanner. So if there's a scanner, there's this build scanner. Okay, so they're kind of building it up. The question is, does it come from that that text file we saw at the top level? I think I was kind of hoping for something that looked like a switch statement or a collection of tokenizers. I'm not seeing it directly. Okay, so the contextual Lexer, it's interesting. I wonder if they're just doing a different style here. Okay. Let's see. I'm guessing this load grammar. Okay, so here they're defining terminals. What is this .lark? Do I see that anywhere? Parsers. Okay, so they've got early LALR, so forth. I don't see a .lark file. All right, well let's go back to that file, load grammar, real quick, and then we'll go forward with either fixing our Lexer or just starting to build the parser. Okay, so these are terminals, basic characters that it cares about. Okay, so so these are the terminal mappings. So this is a regular expression matching, or that's a raw string, sorry, matching the open parenthesis, and here's, okay. So they also have curly braces. Interesting. And they're parsing op as plus or star or the question mark That is a really interesting expression. I'm assuming this will become a regular expression, which would say you have plus or star, or you have the question mark followed by either followed by another question mark, a bang, or A to Z. Okay, we're gonna have to see what that means. Okay, so there's a colon, there's a comma, there's the vertical bar, there's a dot, okay, tilde. All right, so a rule is bang question mark, either an underscore or a question mark, and that is optional, and then A to Z, or A to Z 0 to 9 with underscores. Okay, so terminal is optional leading underscore, caps A to Z, and the extension. This is interesting. Okay, and then there's strings, which we haven't dealt with yet. So that's a pretty typical construction, which is you have an opening quote, and then you have either a quote or an escaped quote, so slash quote, a slash slash, or anything that's not a quote or a line return. And then that's the what is the optional greedy regular expression. It's like take as many but give back, I guess. And a case insensitive. I think that's what that is. No, I is an optional I character after the string. I don't know why that exists, but that's interesting. Okay, and then regular expressions, they have you have forward slash, and then look. What is that? Giving back negative look ahead. They're using some crazy regular expression features here, but say making sure there's not a slash next, and then it's either an escape slash or a double slash, or anything that's not a forward slash. And so this is a very similar thing to this stuff, and then it can have flags after it. It looks like, yeah, percent or s any number of times. Oh no! I'm sorry. They're escaping this re flags thing. IMSLUX. Okay, so those are the available flags for a regular expression. Okay, and then they're combining new lines together. White spaces, space, or tabs, and then so a new line is like take the optional carriage return. Definitely take the new line, any number of these, and then any white space that follows. Okay, and then plain white space without new lines is space or tab. Comments is / Okay, so I don't know that this is actually the same language, but then they've got some rules here, which looks like a more traditional grammar. Okay, so let's go back to the Gleam code. This is interesting in that I think that we could probably we, 'cause, 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 ' we could probably learn some things from it to improve our Lexer. But for now, I think what I want to do is look at I want to look at what they're using here for see if we can get a so we can get an idea of how to interpret these identifiers. Okay, so let's back this off, and let's make our own thing kind of based on variable, and then we will I think what I was hoping to go for here was what is allowed in what is allowed in identifiers, and I don't think that I got that answered. Unfortunately. Because I think if, for example, if this op matched, you would have strings that look like star or plus, and then question mark followed by question mark, bang, and a letter. And I don't, that doesn't seem right. So there's something that I'm missing here. Okay, so maybe we don't modify this for now. Let's look into creating a parser. So I'm gonna have to go back to the nibble documentation. So if we go here to the introduction, readme, is there nothing on that page? There's nothing on that page. Parse context, nothing on that page. Backtracking, nothing on that page. Interesting. Okay, so let's go back to the readme. Okay, so you take you construct little parsers like let int parser be this function, and then you build them up from the bottom. So your parsers know how to transform a list of tokens into whatever you want. You have the full power of Gleam here, so you can go wild. Okay, use take map to consume only certain kinds of tokens and transform the result. Okay. So we can do some of those. So let's make a new pub fun parser or parse. Okay, and this is going to take it's going to take this tokens, and it's going to return a result of an elif program, or for now let's say nil. What did I do wrong? need another paren there. Okay, so we'll put to do in there. Now, let's think about what the very basic ones are. So we're going to make a variable parser, which honestly is just going to check whether it's an identifier. So maybe there's an easier construction for you want to match. All right, yeah. So we can say nibble.token. Okay, so let's see what's in this top level. Okay, it's a sequence. So token returns nil if the token is the next token in the input stream, fails if the next token is not that. Okay, so this will be useful for doing things like parentheses constructions and so forth. Okay, that's not exactly what we want. Okay, so return just returns a value, sometimes called succeed. Okay, so this would be like when we compose some things together, we're taking advantage of the use syntax. Yeah. So maybe what we do, rather than making these like anonymous functions, let's make and this is going to return a parser. I'm going to have to import nibble parser. So this is going to return a parser. And what is this type? Okay, a parser has 3 type parameters. So A is the type of value that the parser knows how to produce. So this will be a variable in our case. Toke is the type of tokens that the parser knows how to consume in the context. Okay, and I don't know that we care about the context right now, so we're going to say this is going to return elif dot, and we need to look at, so program has a body of expression, so this is going to return an expression. So maybe, yeah, so this is going to return elif.expression, and the type of token is the question in my mind is, does this need to be lexer.token? In which case we should make a type alias here, just to make typing that a little bit easier going forward. All right, let's assume that it's this. In the meantime, I'm going to look at the implementation of this. Yeah, of course, something's wrong with you. Yeah, it doesn't understand Gleam yet. So if I look for fun token, okay, right. So this is the inner token type, I believe. Yeah, the parser is opaque type, which contains a function that takes a state and returns a step with a value token context. Okay, so yeah, this token type, we really don't care about the value. If I look at the right, so they're using the inner type here. So like this is the token type that the example defines. So they're using the inner type, not the Lexer's token. So I think that here we'll do token, and then we don't care about the context yet. Okay, so this function that they create here is a parser. Let's look at that do function. That's interesting. Honestly, we could jump to it. Okay, so do takes a parser. Right, so this is for chaining things with use syntax. So it takes a parser and then a function that receives a value and returns another parser. So with the use syntax, you can unroll it so it's flat. It's very much like monadic do in Haskell. So yeah, so they're saying like this is you're returning from this a function, or a parser rather, that contains this as the body, and it's like, you know, run the parser with this state, and then if you get continue, then yeah, so that's what the do does. Then is like a shorter version or an alias. So what they were doing in the example, go back there real quick, is, oops, I don't want to edit that. This is take map. So if we look at the token, let's do something like that. So nibble take map returns a parser, right? So we'll follow their example. Nibble take map. Expected, we'll say expected variable. I don't know if we're going to continue to use this, but we say case token is identifier. Then we'll return some token, and let's ignore what the contents of that is. Otherwise, we'll return none. So what's wrong here is just saying that it's never used. So this is correct, but we're not doing this right. So what we should be doing is going elif dot var and putting right. So we've turned the token into an expression. Now what's wrong? Okay, so we need to import Gleam option some and none. Okay, so we want to turn our token into a variable. Okay, so let's think about what are the other things that are in our language. We could have integers, so let's look at that. Now likely we will be combining these into a expression parser. Token nil. Okay, so we'll do this again. Expected integer. If it's an integer, then we want to return some elif dot int, right? So that creates an expression. Otherwise, we want to return none. That one's straightforward. Okay, so we've covered the base values. Now let's build some stuff that's a little bit more. Well, let's cover booleans. Yeah, that'll be good. So boolean parser elif dot expression token nil. And what I'm going to do over here is I'm going to pop this out to the right so that we can see it, because like this is the thing that we're trying to construct, right? So we'll likely have a parser for expressions, which we built out of these very simple terminals. We'll have a parser for primitive operations, and yeah, we'll probably have a. So we construct these directly, so that can go directly into here. But we'll go ahead and do that. And the parser for program will just call the parser for expression and wrap it. So that'll be easy. Okay, so Boolean, that should do the same thing that we've done here. Expected Boolean. Where are we using this I value? Oh, that's in the type checker. Okay. So we'll do B, otherwise we'll do none. There might be a better way to Okay, so Boolean, integer, or variable. Those are our basic values. So let's think about primitive operation. Now, primitive operations always have parens. So what we can do potentially is combine some of the inner parts with like a one of. So this is going to return a parser, which is an elif.prim op. Yeah, that's going to take tokens and nil. Okay, so let's look at some of their. Here's a sequence type parser. And I think let's go back. Oops, I didn't want to do that. Did I have history here that we were on their documentation? Yep. Okay. Let's look at the documentation. Any. Okay, and it returns any token. One of. Okay, so we're gonna do a list of parsers. And so let's do. This will be the inner. Like, so if you can imagine, these all start with parens and end with parens, and then there's the inner part. And we need to be specific about that because we have we want these tokens, like, so it's going to be read, or it's going to be negate, or it's going to be plus, so forth. And then the the inner expressions. So we're going to have to, let's do expression as a parser. Okay. I might want to make these public at first so we can test them. That would be really useful. So the question in my mind is, maybe we don't want this take map. Take the next. Okay, so this returns a parser. Oh, okay, yeah, that's fine. That's exactly what we want. So if it doesn't match, so if it gets, let's look at the implement. Gosh, dang it. That's annoying that it doesn't jump to the correct thing. Okay, so. Okay, so if you return none, then let's see. No, I'm sorry. If there is a token and then none, it says fail and expecting this, got that. Okay, if you return some, it says continue, and then, with the contents of that option. Okay, if there's no token, then this can never match. That's why this is a fail there. It's interesting this is not backtracking. So those are a bit greedy. However, if we look at one of, all right, this is most useful when you want to quickly try a few different parsers using one of. Okay. Yeah. They're talking about backtracking, and yes, you don't want to backtrack if you can avoid it. Um, but let's find the actual one of implementation. Okay. Right. Okay. So this is saying this is returning a parser that starts with assuming things fail, and it uses the list fold until. So if we look at the Gleam standard lib, list fold until. Right, so it has this continue or stop thing with the accumulator. So I want to make sure that I'm understanding how this works. Right, so you say, you know, if it says continue, then you list stop with that result. If it's fail and you can backtrack, then you stop with the result. If it's fail, then you run the next thing and do list continue. So it's basically saying try each of these until one of them says, yep, I match. Okay. Sometimes these use constructions, especially when they're nested like this, can kind of break my brain. But I've done enough like pipes in Elixir and so forth that like I'm starting to get my brain wrapped around this. It's very nice, and I think at some point I'm going to do a little short about use and about pipes that I'll put up on my YouTube. Okay, so back to the code. So what we want with an expression is we want one of. So this takes a list of parsers. So here, an expression will have, we can have an integer, right? And I think we need to call that. So it's a parser, right? Or we can have a Boolean, or we can have a variable. And those are the simple ones. And then we're going to have a primitive, and let's do. This might be a mapping, because I think that we want to do prim op, and then maybe what we do is we do expression here, and then we do a map over the result of reading the prim op. Yeah. So we might use some piping or use or something like that. Okay, so we'll have primitive, or we'll have I'm gonna have to name this let expression, and we'll comment it out for now. And this needs to be a list. Okay. And then we'll have if expression. Mostly because I don't want to conflict with keywords in Gleam. That's interesting. Let's just join those two lines together. Okay, so those will be our, it's going to be like an expression matches one of these things. Okay, so for, we've already got int and Boolean and variable covered. So let's look at chaining things. So we're going to do use, and we don't care about what the sorry, I want to look back at the example in the README because they do this. Yeah, so they use ignore and then do. This is the do's for chaining. So we want basically a manual sequence of a token, and we'll make use of this. Oh, that's what that return is for. Nice. So we could use return in primitive. Yeah. Okay. So we're going to do. So we'll use nibble.token L paren, and this needs do. So let's import nibble do. So see, they're saying here that this returns a parser, but what we want is to chain it. Okay, so we'll, and then we're going to use prim op is do, and we'll make a parser which is just primitive operation, and then we'll use, we need to consume the token rparen, and then we'll return, oops, elif.prim primop. Okay, so we need to import that as well. There is a risk here of like someone looking at this and going, is return a keyword? No, it's just a function. So that this covers now. We could potentially inline each of these primitive operators. We could say do something like this: nibble one of. Yeah, no, let's make it its own. Let's make it its own parser. It won't be that bad because we're going to okay, so we're going to probably have to make parsers for each of these except for maybe read, because they're going to kind of look like this or some combination of, you know, keyword and then expressions. So let's do, yeah, we're going to say nibble one of. This is a list. We'll say read op or negate op. In some ways, I feel like I should have gone from bottom up a little bit on this construction, but my brain so often works top down. Plus op minus op comp op and op or op not optimal for sure. Okay, so let's actually inline this. Yeah. So read op is simple. It's like parser elif dot primop. this is similar to this. So because this one only has one token that it cares about, expected read. elif.read. None. Okay, now it's just complaining we don't use it. That's fine. Okay, so negate op is going to be the first one that's going to be a little bit different, and I think that it has only one nested expression, so so we can get an idea of how that will work. And I think we're going to do like we did in the honestly, we don't need take map here. This could just be nibble.token, right? Because we want, not elif negate. What is the keyword there? Keyword minus. This will be do. This read op, yeah, it can just be nibble.token. Except I think we need to map it. We'll return elif.read do. Okay, so that's a little simpler than the take map, because that read is a concrete token. It doesn't have, it's not like variable or integer or boolean that contains some other value. I mean, keyword does, right? But read as a primitive operation, like we can directly construct this, so we can say, hey, it needs to be exactly this token. Okay, so for this one we have minus, and then the problem with this is I think we probably need to make sure that minus comes before negate, because these share the same operator. One has one argument and one has two arguments. So negate has, and this is expression, do expression, return negate, negate. So you can see we chain here the minus and then the inner expression, and then we wrap it in a negate, and that becomes the prim op. So I think that we need to do minus op first. And one thing I'm not sure of, I don't think it needs backtracking, because if we put this one first and it fails, then it's going to start over at the beginning of that with the same set of tokens and try that one next. So I think as long as it comes first, it's fine. So we're gonna copy this, and we'll call this arg1, arg2, and then we'll return elif minus arg1, arg2. Okay. Now we just need to do the rest of these. And honestly, we can use something like this. This is very similar to minus, except it's going to start with a different operator. Plus. Okay. Okay, and let's do comp. So this one, we're going to have to do okay, so we have comp as a token type. So we can't do nibble token here. What we can do take map. Expected comparison op. Okay, and this is going to be token, and then we'll do case token of comp. I'm not sure that this is correct because we need maybe what we do is we define a expected 2 arguments got 1. Yeah, the problem is this becomes not in scope. So if we think of it like I'm it feels like we need to do this piped to do. What's wrong there? Okay, so let's do parser. Let's do this. Let's put this in here. And then we're going to do so this type this parser will be like the one of these. I'm missing some parens somewhere. Okay, we're gonna extract that. Comp. It's not. The problem is it's op. Let's call it comp inner. I don't have a. Right, because what we want is this inner thing. So then we do what am I missing up here? Oh, I'm missing a bracket. Okay. So we'll do use op is do comp inner. What I was trying to do is like inline that, but that's fine. So it's like we're saying here we need to consume an operator and then 2 arguments, and then you construct the comp from that. Okay. That was way more complicated than it should have been. Okay, so now we're just missing and or not. Okay. And those will be really similar to plus and minus, at least and or will be. So let's do that. Now, one thing that we could do is define combinators that like take a keyword. This would be over engineering it, of course, but like they take a keyword or like you know, an initial token and then 2 arguments. So like a 2 arity, you know, primitive op, or a 1 arity primitive op, or you know, comp is kind of special here. Okay, and then we have not finally. And this takes a single expression. And I need to fix this. This is or, this is not, and that takes expression. Okay, so we have all of the primitive operations here. And really, I mean, these are like, take the tokens, transform them into a data structure that is part of our language. So now we have primitive. So let's do let expressions, which will be looking really familiar because it's going to be kind of like a lot of the things that were in primitive op. So yeah, let's do the top. Honestly, ordering doesn't matter that much to me in the file. So this is a parser that's going to return an expression, token or no. Okay. So we need to consume the opening paren, right? We need to consume the keyword let. Come on. Okay, and then so let remember looks like let identifier expression. So that's what we're going to use there. So we've gotten open paren and let. We need another open paren. And we need a left bracket. So here's our ID. We're going to do identifier. Or I said variable. Yeah, that's okay. The thing is, we don't actually want to transform it into a variable. We just want to consume an identifier. So honestly, I should still be looking at the docs. Keep them open in addition to the repo, because it's not actually that great to look and try to look for this stuff in the repo. Okay, so like token is not sufficient because that requires a static token. Yeah, so I think we want to make an identifier that's separate from variable. Like variables like identifier plus a wrapper that turns it into an expression. So honestly, I think this parser is going to return a string, and we can probably reframe variable like this. No, this is looking really similar. Okay, so that's this. We can do this is not toke, this is ID. Yeah, so if this is we need to do, yeah. So identifier returns a string, which is the contained identifier inside the token. And here it comes out as a string, and then we pop it into a var. But up in let, we just want the ID. So we're going to do identifier, right? And then where are we in the sequence? Here. So we need an expression. We'll call it binding expression. And then we're going to do the close parens for that. Oops. These will be r bracket r paren. We're going to need another r paren at the end. So, okay. And then we need another expression. Okay, so now we can say if all of that succeeds, we can return let, and let takes the var, which is ID, the binding, which is an expression, and the expression. So I'm going to rename this to var, and then it becomes a lot simpler to construct that. Okay, that's kind of cool. And let's do the if expression finally. And then we'll finally make a program parser, which is going to be really, really simple. So we're going to have to do a lot of the same stuff as what's in let. So let's copy it. So this is keyword if and not keyword let. There's not these particular things, but what we're going to do is we're going to have condition is an expression. We're going to have if true is an expression. And we're going to have if false is an expression. And this will be if condition, if true, and if false. So that one's actually simpler than let. Let was complicated because of this business. Okay, so that's our expression parser. And then our program parser is going to be a parser that returns program token nil, and so this will be use expression return elif dot program expression, and let's rename that to body, and then it lines up. Okay, so now how do you, let's go back to the README probably. Yeah, how do you hook those up? You do nibble.run, give it the tokens and the parser, and it returns. Let's look at what nibble.run returns. Okay, so it could be a list of dead end. So we'll probably want to map that error into something useful. What is this dead end struct? So this is, dead end represents a point where a parser that had committed down a path failed. It contains the position of the failure, the error describing the failure context stack for any parsers that are run. Okay. Okay, so error could be, yeah, let's do it real simple for right now. Rather than nil, let's use their list of dead end. Dead end, and that takes a token and a context, and here is, that's our token and our context is nil. Okay, so basically what we can do is call run directly in here, and so this is just nibble.run tokens program. And that type lines up. Okay, this isn't the greatest, for sure. We could, we want type dead end, and then we don't have to qualify it. Okay. So that was a lot. Let's have a look at making some tests for this. So we did test the Lexer, I believe. Yeah, we made a test for the Lexer, so it was just called tokens test. Okay, let's go in here. So we can take some of this stuff and like this realistic example and see if it gets us the program we expect. And I think we have this program somewhere in abstract form. So let's say parse test. Okay, so we're gonna say, oops, this is going to be tokens, right? And we don't need to do this, but we do need to do should be okay. Okay, so that's just making sure that we can tokenize this program. And then we'll do parse. And that should be okay. Now let's start with that. And if it's not, then we have some things to fix. So, okay, so let's run that. And I'm guessing this is our first pass. It's not going to work. Okay, so we got a failure. We got dead ends. Okay, so that's saying, you know, it got lparen, it was expecting an integer. That's the integer parser failing, expecting boolean got lparen, expecting identifier got lparen, and then expected keyword read got keyword let. Okay, that's fine. Keyword minus got keyword let, and so forth. So let's see. It's still trying to consume the let that's at the front. Okay, these are all the primitive ops. Okay, so did we... I think probably what we need to do is move let expression and if expression before the primitives, because yeah, let's give that a try. Okay, we're getting a different one. So we may need to use backtrackable. Yeah. So maybe what we want to do is rather than backtrackable, because the problem is that let, if, and primitive operations have the same prefix, which is open paren. So I think what we want to do is pull that out and say, I want to say call, but let's call it nested for now. And we'll do nested as a parser that returns elif.expression token nil. Okay. And this is going to be, we're going to pull this out such that it branches only on the first token, right? And then we'll do this, and we'll still have the inner part return an expression. Nibble.oneOf. And that's going to be if expression or let expression or primitive, and then we'll return expression. So there we've got we're taking the parenthesization out of it, and maybe we shouldn't take the wrapping parens out of it, but all right, so this is okay. So let's give that a try. That was the recommendation there, and that will mean we don't need to use backtrackable. Okay, so now it actually parsed. That's great. So what I want to do is now that we parse this correctly, or it succeeded, we didn't say it was correct, I want to get the equivalent program. And so this, needs to be a program, right? And I think that we have this somewhere. We just have it in here. Oh, here it is. Okay, so we're gonna just grab that. We'll say this is Can I do that? Will that work? That'll work. P. Okay. Okay, so that correctly parses. That's great. We did learn some interesting things here. For example, that needing to make sure that the things that share the first token, you need to match that first. That means that you don't have to be have backtracking, which is expensive. So it makes sense to me in my experience with parsing that that's something you want to do. Okay, that's pretty awesome. I feel pretty good about this. Let's see if we can clean this up at all. We could consider doing combining the variable thing with the keywords, especially around that EQ question mark issue. But I'm not sure how much I'm up for with that. Anyway, I feel pretty great about this. We could, well, when we go and do the next chapter, which I think we may do either next week or the week after. We'll take advantage of this parser and we'll add things to it. And you know, we'll keep this up to date with what the capabilities of our language are, and it will mean we'll have to keep changing this as we go. But let's wrap this all together, and in here we're going to, rather than construct this, we're going to pull out this, and let's add parse. I think we can just slurp up the example string here. Okay. We will do we'll say let input is this. Okay. Import Gleam result. Okay, so this is a list of tokens, and then we're going to use honestly, I think we should actually do let assert rather than try, because this function doesn't So this function doesn't return a result, so we don't need that. We can just do let assert, and that's probably better for this example because we're already doing let assert down here. Okay. I'm going to move this up as one of our examples. So essentially this should equal this, which we already demonstrated in our tests. So let's just make sure that all still works, and we'll do Gleam run, and we should get the x86 output from plain text list B through all of our passes and out to the console. So pretty snappy. That's good. And this, I'm not going to double check everything here because we double checked that last time, and we know that this is the same, not last time, but the time before, and that this is the same contents and comes out as the same program. So feel pretty good about that. And I think this is, even though we're finishing up a little bit early, we have a parser, and that feels really good. And we can do so next time or the time after, we'll get back to chapter 5, which is about introducing loops, and that'll have interesting implications on our control flow graph, because now you have cycles. The other thing that we could potentially do next time is something I've been wanting to do for quite a while, which is get all this ready for JavaScript and make a little Lustre app that embeds this and makes a playground that lets you write, this stuff, write the text, and then see the assembly output. I think that would be really freaking awesome. The other thing that we could potentially do there is if we have a way, we could have it stop at particular phases, say like only do up through shrink, or only do these many steps, and then we could have it, rather than print out the text of the text of the assembly code, we could have it output a data structure. So that would be really interesting. I don't know how much Gleam has in terms of being able to pretty print things. There is, the Gleam IO debug bit, but actually debug has been removed. What we could do potentially is build something where we have each of these intermediate languages be able to pretty print themselves, and that's a possibility. So, Lexing and parsing, done in 2 sessions. I think that's pretty awesome. And I'll make a commit and push this. So we have working parser for if language. I still think that we could probably make the Lexer a little bit better. But this will work for now, and as we add new things, it'll be straightforward to add, for example, new keywords like while, begin, that sort of thing. So let's push that, and we'll call it a day. Thank you for sticking around if you're here, and we'll see you next time. We'll either do, like I said, we'll do the compiler playground sort of thing, or we will do chapter 5, which is loops.